All right, so it is Monday, September 23rd at 7:03 p.m. And we're going to go ahead and pick up where we left off. But before we do that, I want to cover a couple things I've been asked questions about. So with respect to the certifications with Cisco changing, they actually have a migration tool that you can use to see if you've passed certain CCNP exams, like if you pass route and switch, what does that mean? Or if you've passed route and T-shoot or switch and T-shoot, or if you've passed all three, what exactly does that mean? And so let's go ahead and take a look here. If you were to just simply go to cisco.com/next level, that's NEXTLEVEL, it'll bring you to this page here. You would then click on certifications. You're going to click on CCNP. You're going to scroll down to CCNP Enterprise because that's the one that we're interested in. And if you come down, you can see they've got this migration tool right here. So if I click on migration, you can see that the CCNP routing and switching migration tool, it explains what's going to happen here on the 24th of February. And that's that new certification exams are going to be released by Cisco because they're getting away with the route. They're going away from the route exam, the switch exam, and the T-shoot exam. But what if you've passed some of these exams, but not all three? Or what if you have passed all three? So let's take a look. So if I click on route, you can see it says, if I've only passed the route exam, to earn the new CCNP Enterprise certification, I need to take these exams. So I'd have to take the core exam, and then I would pick from one of the specializations. Now, what if you've passed route and switch? So here's the nice thing. If you've passed the route exam and you've passed the switch exam, but not the T-shoot exam, you are given the Cisco Certified Specialist Enterprise Core certification. So then all you would have to do is earn one of these specialties on top of that. So you don't have to pass the T-shoot exam, right? You only have to pass route and switch. Well, let's say you've only passed switch. So if you've only passed one of the exams, you can see that, for route and switch, it doesn't give you anything. If you've only passed route, right, you still have to take the core exam and then a specialty. If you've only passed switch, you still have to take the core exam and a specialty. But if you've taken T-shoot, they give you the Cisco Certified Specialist Enterprise Advanced Infrastructure Implementation certification, but then to earn the new CCNP Enterprise, you have to take the core exam. So it's a little quirky. So if you've only passed route, you have to take the core and then a specialty. If you've only passed switch, it's a core and a specialty. If you've passed T-shoot, they give you a specialty. You've got to pass the core. And then again, you saw if you have both route and switch, you get the core, then you need a specialty. And if you have all three, you are a CCNP certified, or you have the Cisco Certified Specialist for the core and the Cisco Certified Specialist for the Enterprise Advanced Infrastructure Implementation. So this is a nice little tool that'll allow you to see if you've passed a couple of these exams or all three, what certification you would end up with. Now, okay. So we've covered the certification track thing. And again, remember, that's going to be February 24th of next year. All right, so let's pick up where we left off last week. And if I bring out the drawing that we had, so here's the drawing that we had, and I kept it from last week. And you can see we had router 1, 2, 3, 4, 5, and 7 in autonomous system 2, 3, 4, 5, 7. Router 1 is an autonomous system 1. And router 6 is an autonomous system 6. And so what we want to focus on this week are primarily the BGP attributes, because these can become very, very confusing, because the IGPs, or the Interior Gateway Routing Protocols, don't have attributes that we can manipulate in the way that we manipulate the BGP attributes. So the first thing that we want to do is let's take a look at this document. And so this document here can be found. If you were to simply Google Cisco BGP Best Path Selection Algorithm, you should find this document right here dated September 12th, 2016, or at least that's when it was last updated. The document has been around for a very long time. And this is the Bible when it comes to the BGP best path selection algorithm, and it does a much better job than the textbook does. The textbook does a very good job, and it shows you a lot of the different details. But this actually opens up, and it talks about why routers ignore paths, right? Okay, if the next hop is inaccessible, that path is going to be ignored, right? That BGP mandatory attribute, next hop. And we'll talk about the mandatory attributes and the other attributes that exist. So this talks about why a router may ignore a BGP path. But then we get down to how the best path algorithm works. And I'm going to give you examples for a number of these. Now, the first one is wait. And to be clear, they call it out as a Cisco attribute, and that is true. It is not a BGP standard attribute like local preference or AS path or MED. Wait is a Cisco specific, and it's really not, I don't even like calling it an attribute because then it gets people confused with being a BGP attribute. It is a Cisco specific parameter. Now, you're going to hear that this is Cisco proprietary in some places. And while that is true, Juniper implements wait just like Cisco does. So Juniper's not stupid. You know, they know that Cisco is, you know, the 800-pound elephant in the networking space, and Cisco implemented this feature called wait, and it actually makes sense. When we look at the use case where you would use wait, it makes sense. And we've got two opportunities to do that with Autonomous System 1 and Autonomous System 6, and we'll do it with both, right? So wait is the #1 criteria that is evaluated when a router running BGP is trying to determine the outbound path it's going to take, or the egress path. And this is critical because when we talk about control, right? You control, right? And that's the definition of the autonomous system, is that it's under an administrator, the same administrative control, right? So for traffic leaving my autonomous system, I have 100% control how that traffic is going to leave my system. And that's even if the traffic is transiting through my autonomous system. Once traffic in a BGP context enters my autonomous system, I now control how that traffic will egress or exit my autonomous system. And with BGP, we go down the best path selection algorithm to determine how that's going to happen. So let's take a look at router 1 right now. And if we remember from last week, router 1 should be learning a route from router 6, which is way down at the bottom of our topology. And we can see that sure enough, oops, sorry, the mouse ran out of space there. Sure enough, we've got 2 paths. But remember, BGP is only going to pick one best and valid path, right? Or maybe I should say valid and best path. So it's only going to pick one best path. And that's what we see with the asterisk indicating valid, the greater than indicating best. Or you can think of it as pointing to the best path. Now, the question should come up, well, why? Why on router 1 did BGP pick this path with the next hop going to 169.254.12.2? And so again, every time BGP receives NLRI, or network layer reachability information, it's going to go through this best path selection algorithm. And so, let me flip back here and clear the screen real quickly. And so it's going to walk down this list of criteria to determine which path is the best path. So it's going to look at first the wait, right? Because remember, I'm saying, how am I going to egress? How am I going to get to that network? In other words, how am I going to exit from my autonomous system and go to that network? And right now, it says we're going to use router 2. Now, we look at the wait. So let's come over here and look at the wait. what is the weight value for both of those paths? And under the weight column, we can see here it's 0, 0. And by default, the weight is 0 for routes that we do not originate. When we originate the routes, like the 1111 on router 1, the default is 32,768. And you can clearly tell here, and you can also see the next hop is quad zeros. So when you see quad zeros and 32,768, it's clear that you originated this route. However, here, we did not originate the 6666, right? That came from Autonomous System 6. So BGP looks and says, okay, well, the weight is 0 for both. Higher is better with weight, so it's a tie. So I now move down to number 2, local preference. Now, this is kind of tricky. You'll notice that local preference has nothing here. Even when there's nothing shown for the local preference, the default value is 100. In fact, if I was to say show IP BGP for the 6666/32, there's the proof. The local preference, even when it doesn't display, by default, it's 100. But it's 100 for both. And we'll come back to this command because you can see here, that tells me that this one is the best. Now, it would be great, and I don't know how difficult it would be to add it to the code for BGP on the Cisco platform, but wouldn't it be great if it said best and then told you why it was the best? Unfortunately, it doesn't, right? And so it forces you to have to go through this process. So the local preference is 100 for both paths, both egress paths out. So then I come down here to the third choice. And the paths are sourced by the network or the redistribute command, right? That's not applicable in our case here. The path with the shortest AS path. So now I come down to the autonomous system path, and you can see it's the same. It's 2 is the AS path length. So BGP says, okay, the 4th criteria is a tie. I go to the 5th criteria. Prefer the path with the lowest origin type. All right, well, if we come back over here, we can see that the origin is IGP. And you can also see that over here. Remember that little I that kind of ends up at whatever the end of the AS path is, and there's no column header here that says origin. You just have to know that it's I, meaning it's coming from IGP, because we originated it on router 6 with the network statement. So BGP says, okay, it's the same origin code. Now I'm going to come down and check for the lowest med. Well, we look at the med values or the metric, and you can see that the metric values are blank. So there's 0 by default, right? And in fact, if I come back over here and we scroll down, it's not even going to show you that the med is not even set, right? So, and I'll talk a little bit more about med later. So the default for med is 0. However, it's not set here at all. So there is no med value that's going to be displayed. And we'll talk, and med is one of those attributes that is not used just simply because look at how far down it is. It's down in the 6th location. So there's 5 other criteria that are assessed that could trump the med from even being evaluated. And so that's typically why you don't see med used very often. So then it's going to come down here, prefer the eBGP over the IGP. Well, they're both EGP learned routes, right? So we skip over number 7. Prefer the path with the lowest IGP metric to the next hop. Well, that doesn't, we're not doing that here, right? We wouldn't be assessing that here because there is no IGP metric for me to get to that next hop. Determine if the paths are doing multipath. We're not doing multipath, so that doesn't, we're not going to evaluate that. When both paths are external, prefer the path that was received first, right? So it might be the path that was received first, or it may be the originator down here, I'm sorry, number 11, prefer the route that comes from the BGP router with the lower BGP router ID, right? Depending on whether the path was received first or the lower router ID. And so if you look here, if there's any kind of flapping or whatever, typically is you're going to have a selection criteria before 10, but if you leave it by default, chances are it's going to come down to either 10 or 11, right? Where it's either the lower router ID, and in this case, this is the lower router ID. The router ID for router 2 is 2222. For router 3, it's 3333. And so, let's see what we have here. All right, so this is our best, right? Based on lower router ID because the route was learned from both of the other routers at the same time. So now we want to manipulate, right? And this is what the BGP policy is all about. We want to manipulate how the traffic leaves our autonomous system. So if we look at that drawing again, sorry about that. If we look at the drawing again, we want it to go out this path here. So we want it to go to router 3. Right now, the default is router 2. So on a Cisco platform, and you'll notice here, in this autonomous system, I have a single router. There are not multiple routers running BGP, and this is the use case for wait. If you have a single router that has multiple connections, right, multiple BGP peerings, and it doesn't matter, it could be, this could be, I mean, we could be connected up over here to some other BGP neighbor, and we could be connected over here to some other BGP neighbor. We can use wait as a very quick and easy way to say either all traffic go to this neighbor or specific traffic go to this neighbor. And we're going to inject another prefix off of router 6 here in a second. So the first thing I'm going to do is I'm going to show you how we can pick router 3 for all of our egress traffic, right? And again, we have full control over how, and I did not want to do that. Hold on one second. There we go. Whew, close call. And we want to control the egress flow of traffic from our autonomous system. So let's see what it looks like. Do show run section router BGP. So here's my BGP section, or my BGP stanza, configuration stanza right here. And it's super, super simple. I would simply say neighbor 169.254.13.3, and I can set the wait. And as long as the wait is greater than the weight of the other path, and they're both 0 right now, so I could put 1. And again, the range is 0 to 65,535. And I'll do a question mark, and there we go. We can see that. So if I said wait 1, and I hit enter, and I say do show IP BGP, let's take a look. All right, you can see it still likes the path through router 2. Right? And you may be saying, well, wait a second, you just said that if the weight was higher, excuse me, that it would take the path through router 3, that the greater than sign would show up here on this line. And you can see the weight still shows 0. And this is where BGP, again, that slowness of BGP. So now we're going to cover how you would refresh BGP. And you can do it in, there's a couple different ways you can do it. So I can say, do clear IP BGP star. Now, if I hit enter right here, this is going to be a disruptive change. Sorry. This is going to be a disruptive change. And this is going to tear down the adjacency or adjacencies that I have. And so we don't want that to happen. And you certainly don't want to run this command in a production environment. So if I say do clear BGP, IP BGP star in and then out. And what that does is it rereads the adjacency rib in and the adjacency rib out, or ribs in and ribs out, for this router. It basically just refreshes everything, and it does it in a non-disruptive fashion. So now when I say do show IP BGP, we're going to see that the greater than sign has now moved, and there's that weight value, right? And you can see that it just has to be more than the other peering. Now, this is for all in LRI. So let's come over here to router 6, and let's say that the administrator over here, and I should say autonomous system 6, So, and the administrator here says, I'm going to create interface loopback 66, and we're going to say IP address 66, 66, 60, oops, sorry, 66, 66, and we'll make it a /32. I'm going to say router BGP 6, and we're going to say network 6666 with a mask of all 255s, right? So I've just advertised out this new prefix. So let's come back over here to router 1, and we'll give it a second, right? BGP is notoriously slow, but we are going to see that update. It's got to make its way through that transit autonomous system, and I may have to go over and give it a manual kick here. And actually, let's see if we can force do clear IP BGP star in, and let's see if the holdup is here. All right, we're going to have to go into the rest of the environment here, and let's take a look and see. Show IP BGP. And do we see the 66? We don't. So maybe we're going to do clear IP BGP star out and in. And so this is one of the things where there's a scanner process with BGP that runs, and typically an update will process immediately when you add new NLRI, show IP BGP. And we are not seeing it. And do I have a typo here? Oh, you know what? I apologize. I left out, I was thinking 6.6.6.6, and it's 66. And let me get the word mask in there. Sorry about that. So mistaken my network command. And again, typically you should see that the update processes immediately, and there we go. And we see it immediately. And so you can see that now here, right, because we have the wait command, that anything new that we learn from routers 2 and 3, I control how it's going to leave this network. So let's talk now about, well, what if I want the 6666 to go one way, but I want the 66, 66, 66 to go a different direction. So let's say that we want 6666 to go to router 3, but I want 66, 66, 66, 66 to go to router 2 for whatever reason, right? And so here's where we can control how that's going to happen with wait. And the way that I can do it is I can create a prefix list. Remember, so now here we're going to start to see where when we talked in chapters 4 and 5 about doing layer 3 traffic engineering, what that might look like. So I can say IP prefix list, and we'll just call it wait, and we'll say sequence number 10, and I'll say permit 66, 66, 66, 66 /32. So there I've got my prefix list. So now I want to do a route map. So I'm going to say route map, and we'll just call the route map wait as well. Now, if I hit enter right here, remember the default is this, permit 10. So you don't have to type in permit 10 if that's what you're going to use. I can just simply say route map the name, hit enter. So I'll say permit 10. Now I'm going to say match IP address, prefix list. So I'm going to match that prefix list, which is matching the 66, 66, 66. And remember, I'm only trying to match that one route. So I'm going to match that prefix list, which is called wait. And what am I going to do? Well, I'm going to type set ? And you can see that we can actually set the wait. So I can do it if I want all NLRI, if I want all egress traffic to go to one of the other ISPs or the other service providers or the other autonomous systems, I can do that with the simple neighbor command. Here, I want to pick off the 66, 66, 66, 66 because I want it to go to router 2 for whatever reason. Maybe it's a preferred path. Maybe it's, not a leased line that you're paying, per bit, whatever the case may be. So I'm going to say set wait, and we're going to set the wait to something, we'll set to 55555, right? So something that's going to stick out in the BGP rib. So we set the wait to 5555. Now, the last thing I need to do is a route map wait and permit 20. And the reason I have to do this is so that all other routing information is allowed to be processed. So processed without the weight being set. So now I'm going to go back into router BGP1 and do show run section router BGP. So now we take a look here. So now I'm going to be applying, you can see here, we set the weight to 1 with the neighbor statement. But now I'm using a route map. So this is going to be different. So I'm going to say neighbor 169.254.13. We said 2. We want this to go to router 2. And I'm going to say route map weight. Now, this is what gets confusing. I'm setting it in the inbound direction. And for a lot of learners, this becomes confusing because I'm telling you that weight and local preference control the outbound flow of traffic. And that's true. Weight and local preference are the two attributes that control the outbound flow of traffic. AS path and med are the two attributes that can control the inbound or the ingress flow of traffic try to influence the inbound flow of traffic into my autonomous system. So what this route map does is it applies the route map and the prefix list to the routes that I'm learning that are coming into me from that neighbor, which is why we apply the route map in the opposite direction of the flow of traffic, if that makes sense. So we're talking about controlling the outbound flow of traffic. So I'm going to apply the route map in the inbound direction. In other words, the routing information, the NLRI that I'm learning from router 3 that it is sending into me, that is what I'm going to apply the route map to. So I'm going to hit enter and hold on one second. 169.254.13.3 route map weight in. Oh, sorry. Yeah. Terrible with the IPs tonight here. All right, so there we go. Second mistake with IP addresses. All right, so there's the route map statement, and that's the IP address for router 2, right? That's that transit segment IP on the interface on router 2. So now let's take a look. Do show IP BGP, and what we're probably going to see is the 666666 still shows a weight of 1, and you can see here that it's still going to router 3. Now, we know that's not what we want, and in fact, we just applied this route map. Again, BGP is notoriously slow, so what you will do 99.9% of the time is you're going to say, do clear IP BGP star in the inbound direction. So I'm basically refreshing the inbound, the adjacency ribs in, right? And I'm reapplying my policy. And that's what we're doing is we're just applying policy to these neighbor statements, and we're using a route map and a prefix list. So now let's say do show IP BGP again. And what we're going to see is take a look. There you go. And so we've now controlled the outbound flow of traffic. And you can see this is to go back to the statement that I made earlier, which was last week, actually, in the Zoom session last week, we were talking about control versus influence. And the fact that BGP, while, yeah, it's a routing protocol, it's more of a policy application tool is really what it is, because you're not going to be running BGP if you have a single connection out of your enterprise, right? And like at the CCNA level, if you've got, the one router with a single connection to the service provider, you're not going to be running BGP. There's no use case for it there. But when you're talking about a router with multiple connections to multiple routers via BGP or multiple service providers via BGP, that's where you are going to run BGP, and that's where you would end up applying policy like this, right? So that's the weight attribute. So we configured it with the neighbor statement, which is one way to do it. Another way to do it is to simply use a prefix list and a route map. And then there's a third way to do it. You could simply just use a route map without the prefix list, which kind of, if you're going to do that and you're not going to specify the NLRI, then why not just use the neighbor statement with weight, like we did do show run section router BGP. we would do it, you could do it with a route map and not a prefix list, right? Just do the route map, and in the route map, set the weight to 1 for all NLRI, but that doesn't make sense because you can do the exact same thing right here, right? So we're going to do it right here, and then we did it with this route map. So again, that is the #1 criteria that's evaluated right out of the gate to see how is that traffic going to leave or exit the autonomous system. And again, remember, when we're talking about control, you control how the traffic leaves your autonomous system. You can only influence or try to influence the return flow of traffic. And I'm going to show you that in a second here. So the next one that we're going to talk about is local preference. And this is going to make really clear, and we'll do it on router 6, even though router 6 is not the best use case. So wait, let me take a step back real quick. And so let's recap on weight here. So the bottom line is, with the weight attribute, it is not communicated to any other routers, either internal BGP peers or external BGP peers. It is locally significant on the router on which it's configured, right? And that's why in an environment where you have a single router with multiple BGP peerings to maybe the same provider or multiple providers, weight is an ideal way to tackle that problem, right? If you have more than one router in your environment and you have an IBGP peering configuration set up, right? That's where it's going to become advantageous, where you don't want to use weight. That's where you want to use local preference. And again, we're talking about controlling the outbound flow of traffic. So the use case with weight is, I've got a single router, it's got multiple BGP peerings, and I need to control the egress flow of traffic. That's the use case for weight. The use case for local preference is, I have multiple BGP routers in my autonomous system that are IBGP peers, because local preference is communicated via IBGP to all of the IBGP peers. So that way, if you've got more than one router running BGP in your autonomous system, you can signal to the other IBGP peers, hey, if you're trying to leave this autonomous system and you want to go to this network, or maybe if you want to go to all networks, come to me and I'm going to get you out of here, right? And so that's how you would control it with more than one BGP router in your autonomous system. And so if we look at the drawing, an ideal use case for that is going to be here in autonomous system 23457, right? So right now, what do we have? We've got traffic that is leaving autonomous system 1, right? And the 66, 66, 66, 66 is coming this way, where the 6666 is coming this way. Now, it would stand to reason that when traffic is returning, right? So the traffic gets down here to router 6. And actually, I apologize. Let me real quickly here on router 1, let's see what happens when I say trace to the 6666 and source it from my loopback 0 address. And you can see the 6666 goes to router 3. What about the 66, 66, 66? And you can see it goes to router 2. But it ultimately gets to router 6, and then those packets, they come back. Now, here's where I'm going to demonstrate that you can control the egress flow, right? Like how traffic leaves your autonomous system, but you can only hope to influence the return flow, right? Or the ingress flow of traffic. So we've already determined that these guys are all IBGP peers in here, right? And this autonomous system has 5 routers. Everybody is fully meshed. And so let's say over here that on routers 4 and 5, that autonomous system 23457 has decided, hey, you know what? When we have traffic that's leaving the network and it's going to router 6, we want all of that traffic to come out through router 5. Now, for the 6666, that's the shortest path. That's probably going to make sense. But for the 66, 66, 66, it should go router 2, router 4, router 6. In fact, if we look back right here, you can see it goes router 7, router 4, router 6, right? So that's the path that it takes, is it goes to 4 and then to 6. So we're going to change that. We want all traffic, instead of going 746 or however it's going to get there, we want that traffic all to go through router 5. Now, I could set the weight. However, remember, weight is locally significant. In this environment, that is not going to help me, because there's no way for router 5 to tell routers 4, 7, 3, and 2, hey, my weight value is really, really high, so we're going to go out this way. It's locally significant to router 5. This is the use case for local preference. And so, again, there's multiple ways that we can configure this, and I'll show you a couple right here. So let me clear the screen here. And we said router 5. So over here on router 5, let's go ahead and take a look and see what we've got when I say show IP BGP. Whoops, show IP BGP. And you can see right now that my path to get to the 66, 66, 66 is to go to router 6, and the same thing here is to go to router 6, right? So, but other routers in the autonomous system for the 6666, you can see, I'm sorry, and this is for the 6666. So we're going to force all traffic to go out through, and I think we said router 5, right? Because you can see here, it's going through router 6. We want everything to go through router 5. And I apologize, give me 1 second here. Yeah, so we're going to drag all traffic, and let's take a look real briefly here. Let me make sure that 4 looks like I think it should. Show IP BGP. And what I'm checking for here is to make sure that right now 4, yeah, so you can see right now router 4 is learning that same route from 5, right, for the 6666 and the 66, but it's going through router 4. And you see the local pref value that we're getting here is 100. So watch what happens when I do this. So over here on router 5, and we'll do this in the route map without a prefix list, because again, we're going to force everything to go out router 5. So I'm going to say route map, route map, and I'm going to call it lpref for local pref. I'm going to hit enter, because by default it's permit 10. Okay, so what am I going to do? I'm going to set local preference, and there are the values that I can use. And so I'm going to just do 99999. Again, something that's going to stick out when I say show IP BGP. And again, with local preference, just like weight, higher is better, right? Higher is better. And if there's a tie, it's going to move to the next criteria. So I set the local preference. Now, I'm setting that for everything, and I'm matching everything, because there's no prefix list here. There's no access list that's saying, oh, just match that one route, or just match this range of routes. I'm matching everything. So I don't need another route map statement that says route map, lpref, permit 20, and then hit enter, because that's kind of what this is. This is just saying set the local preference to 99,999 for everything that I learn from router 6. Now, here's the key. Remember, with the weight, it was kind of done the same way, but with local preference, router 5 is now going to notify everybody, and he's going to tell everyone in his autonomous system, hey, I'm the best path to get to the 6666 and the 66. And so let's see what that looks like. So that's it for our route map. So now all I have to do is say router BGP 5. I'm sorry, router BGP 23457. And let's say do show run and didn't want that. Do show run, pipe it to hit section router BGP. All right. So we've got a single neighbor connection, single eBGP neighbor connection here. So again, I'm going to say neighbor 169.254.56.6. I'm going to put my route map statement in here, lpref. Now, again, it's always kind of confusing, and the mnemonic that I've always used is, it's just think opposite. I'm trying to influence the egress or outbound flow of traffic from my autonomous system. Therefore, I'm setting the route map on the inbound NLRI that I'm learning from this neighbor. And I'm going to communicate that to everybody else in my environment. So I set it, but let's come over to router 4, who's also paired with router 6. And let's say show IP BGP again over here. And you'll notice, right? Take a look. The local pref is all 100. Nothing's changed. Remember, and I can't stress this enough, when you make changes in BGP, especially when you're applying prefix lists or route maps or AS path access lists, whatever the case may be, you definitely want to say, if you want it to take effect immediately, do clear IP BGP star in. And again, I'm going to refresh the routing information that's coming out of the adjacency ribs in. I'm going to reread it and I'm going to apply my policy to it, the policy being the route map. Now, when I do that, let's say here, do show IP BGP, and what do we see? Well, take a look at that. So there it is. I see it on router 5. Now the question is, am I telling you the truth? Does router 5 notify everybody else that, hey, that's the way that we should go? And lo and behold, it has now changed. So router 5 is now saying, no, no, no. If you need to get to the 6666, and this is for everyone in his autonomous system, if you need to get to the 6666 or the 66 networks, you will come through me. So router 4 sees it that way. Let's check router 7 out. Show IP BGP. And what does router 7 now say? Who does he see as the best? Router 7 says, yep, my next hop, I'm sending the traffic to 5555, router 5. We take a look at router 3. And router 3 is going to say the same thing. If I've got traffic going to 6 or the 66, we're going to router 5. What about router 2? And so this proves that local preference is communicated to everybody in the autonomous system that's an iBGP peer. And this is the use case, right? Again, I've talked about, like, it always comes down to use case, what you're going to do. And you've got to think of it from a missional perspective, which is, this is what I'm trying to accomplish. What are the tools that are going to work best, right? And so the use case for wait is a single router, multiple BGP peerings. And it could, again, it could be with the same provider, it could be with multiple providers. But if you've only got a single router and you've got multiple BGP peerings, wait's the way to go, right? If you don't have any iBGP peers that you're communicating with, you don't need to set up local preference. You can use Cisco's wait. And again, Juniper, JunoS support, you can set wait on Juniper just like you can do with Cisco. Now, when we talked about the setup here in 23457, we've got 5 iBGP peers in here. Wait is not going to work because wait is not communicated to other iBGP peers. And I'm trying to control all of the egress flow of traffic, right? So now I'm going to show you something interesting. So what's happening here now? So router 1 is sending traffic for the 66, 66, 66 to router 2. And then that traffic is it's going to have to go to 5. So now let's rerun the traceroute commands that we saw earlier and see if they look different. And let's come back up here. Whoops, sorry. Scoot down a little bit. I just wanted to see the trace routes that we ran earlier. right here. This is the one we're looking for. You can see when I went to the 66, I went to router 2, then I went to router 7, then it went back to router 4, then to router 6. So let's trace out to the 66 now and see what happens. Do I go 2746? And the answer is going to be no. So I'm going to say trace to the 66, 66, 66, and source it from loopback 0. Now it's going to go through router 5, right? So it goes from router 7 to router 5. And that's exactly what it should do. If I was to do the same thing and trace to the 6666 and source it from loopback 0, it's going to do the same thing. It goes to router 3, it goes to router 5, it goes to router 6. And again, the key being that all traffic leaving autonomous system 2, 3, 4, 5, 7, we have complete control over it, and we've said all of it goes to router 5, all egress traffic coming out of 2, 3, 5, 7. So again, right, think of it like this. I've just shown you that we have 100% full control over the egress flow of traffic. So now we're going to talk about how you can try to influence the ingress flow of traffic. And there's two ways to control the inbound flow of traffic. I'm sorry, to try to influence the inbound flow of traffic. One of them is the MED, right? And MED is not used very often. Typically, you'll see MED used at internet exchange points between large service providers. That's typically where MED's going to be utilized. And the reason being is, again, it's way down on the, and you can see we've talked about weight, we've talked about local preference. Well, number 4 is the autonomous system path, AS path length. And that's evaluated before the MED is evaluated. So typically what you see happen is AS path prepending, right? Because there's a very important reason why AS path prepending is used and not MED. And again, in the majority of cases, there are use cases for MED. And again, it's typically a service provider internet exchange point type thing, like at the College Park Max, where there's multiple internet service providers peering with each other. That's typically where you'll see it used. But MED will only go one autonomous system away from where it is set. So in other words, on router 6, if I was to try to influence the ingress flow of traffic and I used MED, the MED value would be communicated in here, right? To whichever BGP peer I set the MED on, it would be communicated in here. However, it would not be communicated to autonomous system 1 because it is non-transitive. And that's when they talked about the different, the well-known mandatory, well-known discretionary. They talked about non-transitive. MED is an optional non-transitive attribute, which means it'll get communicated into the the neighboring autonomous system, right? And these IBGP peers will share that information. However, autonomous system 1 will never see that, right? And so when we're talking on a larger scale, you want to use the well-known mandatory attribute, which is the AS path. And it makes sense. I want to use an attribute. If I'm trying to influence things, I want to use an attribute that is 1, mandatory, which means it has to be in the BGP updates that are being sent throughout the internet, and 2, it's well known, meaning all implementations of BGP across all providers, all vendors, Cisco, Huawei, Juniper, HP, Arista, whatever the case may be, Palo Alto, they all have to support the AS path because that is BGP's external loop prevention mechanism. It's a well-known mandatory attribute. And that is why it's preferred over the MED in the majority of use cases. So what I'm going to do right now is I'm going to show you how we can try to influence the ingress flow of traffic, but I'm also going to show you that you can't control it, right? That you have no control over how traffic comes into your autonomous system. You can control how it leaves, how it egresses, but the return flow of traffic, you have no control over that. And if you're not seeing that yet, remember in autonomous system 23457, we set the local preference on router 5. And right now, 23457 is saying, no, all traffic come through router 5 into autonomous system 6. So 23457 is controlling how traffic comes into my network. And maybe that's not what I want. And so let me demonstrate how you would try to prefer a path with AS path prepending. And really, it's kind of an illogical way of thinking about it, because when we do AS path prepending, right, we're prepending or we're adding instances of an autonomous system to either one route or it could be all routes. And we make it look worse because remember, AS path length is how BGP will determine the better path when it comes down to the AS path. So if we get down to the fourth criteria, which is the AS path length, that is what BGP is going to look at. Which path is longer? So let's go on to router 6. Right? And again, now I'm trying to influence how traffic comes into autonomous system 6. And so here in autonomous system 6, take a look at our BGP table here. I'm sorry, I did not want that. Show IP BGP. All right, so we can see that this is what we're currently learning. So here's the 1111. There's my locally originated NLRI, right? So here's how we can do the AS path prepending. So I'm going to say that for all networks that I have originated, which would be the 6 and the 66, we're going to go ahead and I'm going to do AS path prepending, and I'm going to do it with router 5. So in other words, I'm going to intentionally put my autonomous system number, multiple instances of it, on all the update messages that get sent to router 5. Because again, autonomous system 6 in this scenario is looking at it and saying, yeah, okay, I'm going to make the path, I'm going to make router 5 look at the AS path length, and it's going to think it's worse. And therefore, it's going to all come through router 4. But that's not what's going to happen. Because again, remember, autonomous system 23457, they control how traffic leaves their autonomous system. So let's get this set up. So I can go into global config again. I'm going to say, oops, sorry, say route map. And I'll just say AS path prepend or ASPPP. And then we're going to say AS path or sorry, set AS path prepend. So we'll say set AS path, there we go, prepend, set AS path prepend. Now, again, when you're doing AS path prepending, never, ever, ever use somebody else's autonomous system number. Always use your autonomous system number. So 66666. So what I've just done here, and what's going to happen, and again, since I'm doing it for everybody, there's no ACL that's matching specific prefixes. There's no prefix list matching specific prefixes. So it's here that it's going to apply to all of my NLRI, right? In other words, the 6 network and the 66. So we'll go into router BGP6, and let's say do show run section router BGP. And it's in here that I see my neighbor statements. So I'm going to say, I want the neighbor statement with router 5, 169.254.56.5, right, with router 5. And I'm going to say route map and AS path prepend. Now, remember, with weight and local preference, we're controlling the egress, the outbound flow of traffic. We set the route map in the inbound direction, right? And this should make a lot of sense. I'm trying to control the inbound flow of traffic. So I'm setting the route map in the outbound direction. In other words, I'm setting the route map to change the update messages that I'm sending to router 5 that are leaving, that are going out from me to router 5. So I would set it in the outbound direction. MED would be the same thing. I would set the MED in the outbound direction because we're trying to influence the ingress, the return inbound flow of traffic. So, okay, this looks great. So let's come over to router 5 and let's see, does router 5 see multiple instances? Show IP BGP. And here's what this would look like. No, I still see just one instance here of the autonomous system. Remember, with BGP, it is notoriously slow. So do show IP BGP star. And again, I want to refresh the outbound, the adjacency ribs out, right? And I've got a really nice graphic from a different book than our book that I'm going to show you here in just a second. When I keep saying adjacency rib in, adjacency rib out, I didn't want that. I want to do clear. Sorry about that. Do clear IP BGP star out. All right, so we've just refreshed the outbound updates from the adjacency ribs out. Now when I run this command, take a look here. Now, you can see that on router 5, it sees for the 6666 and the 66, it's seeing that we're pre-pending, right? So we're trying to make it look worse because over on router 4, let's see what router 4 sees. Show IP BGP, and router 4 is going to see, right? Because it has multiple paths. And you can see router 4 can go directly to router 6. And if you take a look, and let's just take a look at the 6666 here, right? And let me get my pen up. So take a look at this. And let's change it to red. So remember, router 6 prepended 4 instances. 1, 2, 3, 4. Here's the, this is the original one that was there already. And I prepended 4 instances of my autonomous system number to make it look worse so that router 5 would say, oh, you know what? Let's go, we'll go a different direction. But take a look here. Router 4 still says, I'm sending all my traffic for the 6 network to router 5. And over here, take a look. The 66, it's still going to go to router 5, even though that path has 5 instances now of the autonomous system. So this is where we take a step back and we go to the best path selection algorithm. Sorry, let me flip out of this here. We go to the best path selection algorithm, and let me clear the screen. So we look at weight, we look at local preference, we look at the aggregate, we look at the AS path. Prefer the path with the shortest AS path. But here's the problem. Local preference, right? Remember, local preference is looked at but first, or I should say before AS path. First is weight. But local preference is looked at before the AS path. And remember, on 5, I set the local preference. So that should drive home the fact that I can't control, right? And MED is even further down, right? MED is the 6th criteria down there. So if setting the AS path to try to control the inbound flow, or setting the MED to try to control the inbound flow, it's not going to work if the neighboring autonomous system has said, no, I'm going to set the local pref, or I'm going to set the weight value. We're going to control how traffic goes into your autonomous system. Now, realistically, when you're working with a service provider, there's obviously communication. There's going to be a service provider peering agreement that you're going to set up between yourself and the service provider that's going to hash all of these things out. And any service provider that knows what they're doing is going to have community attributes that are pre-configured on their side. And we talked, I think it's one of the appendices that talks about communities. And so this is the value of the communities that you can set. Verizon does it, AT&T does it, our in-house service provider, InWave, does it, where we will signal when we're advertising NLRI in the outbound direction, we will tag it with a community value. And it's as simple as saying, set community and then whatever you want to set the value to. And let me show you right now. It's really simple to do here. And on router 6, are we in the, let's go back into route map, AS path, prepend, and I'll say permit 10, right? I could say set community. Oops, sorry, I got to go one further. I could say set community, and then I can put the community number in here in any different kind of format. So I could put let's say my AS is 6:200. And what that would do, right? And they'll have it preset on their side, so actually it wouldn't be my AS. It's going to be, it could be any value. It could be, 65,222, whatever. They're going to give you some community value that you set. And when you advertise your NLRI to them, you tag it with that community value. And on their side, it sets the local preference to a higher value. So in other words, the service provider, in our example here, AS23457, would say to Autonomous System 6, hey, tag your routes that you're advertising to us with this community string, right? 65222 or whatever, :50. And if we see that, we will auto-magically set the local preference on our side to ensure that the traffic returns back through your network as you would like to see it come back into your network. And that's typically what happens in larger service provider setups and agreements, is the communities are set up and then you set the local preference, right, by signaling the other provider. And then it sets up local preference on their side and it takes care of everything. And again, it's one of the reasons that MED is not used, is MED is way down there. It's not mandatory. It's not well known, and it doesn't have to be in updates, and it's non-transitive, right? It's going to go to this next autonomous system. If we set it in Autonomous System 6, it's going to come in here to Autonomous System 6. In fact, let's go ahead and set that. Let's set it up right now. I'll set the metric on, excuse me. Let me clear the screen there. So I'll set the metric. Instead of doing this, let me set the MED. And to set the MED, you just go into a route map, and we're going to set it for everything. And there's the metric value, right? So I can say set MED, and we'll just set it to 77777, right? So do clear IP BGP star out, right? So now let's step over here to router 5, because that's the route map we manipulated, is the one that had set up with router 5 here. So do show IP BGP, excuse me. Show IP BGP, and take a look. The MED is now set. In fact, let's go all the way up to router 2, and let's make sure. Remember, I told you that the MED, it's going to be sent into the neighboring autonomous system, but it's not going to make it to Autonomous System 1. But let's come up to router 2 and Autonomous System 23457 and take a look. Yeah, everybody in here is learning about the MED, but you know what? It's irrelevant, because the MED is not evaluated before the AS path prepending that we just did. So, and we've got local preference set anyway. And this is what it's all about, right? Is understanding which one is evaluated, where it's evaluated at, and are we talking about the outbound flow or the inbound flow of traffic? So here you can see the MED is set, but MED isn't going to be looked at because we've got AS path prepending set, right? And that is evaluated 4th, and MED is 6th. So now let's come out here to router 1, because if I was telling you the truth that it's non-transitive, it's going to go to AS23457, but it's not going to make it into Autonomous System 1. I would say show IP BGP, and we're not going to see the local preference value either. Because remember, local preference is something that's shared within the autonomous system with the iBGP, your internal BGP peers. So we're not going to see local preference here. We're not going to see weight here. We are going to see AS path prepending. Remember, that is a well-known mandatory attribute. It's going to be in every BGP update message and has to be honored by all BGP implementations from all of the vendors. So we'll see the prepending, but Do I see that local preference value? And what about the metric? It's gone, right? And this is why med is not very effective. Again, in the majority of use cases, it's not very effective. But we do see all of the AS path prepending. And so you can see here, our choice is for the 6, it's router 3, because for the egress, because the wait is set for 6, and then the 66, we go to 2. Because again, irrespective of what the AS path prepending does, we're talking about egress from autonomous system 1. I control that, right? So hopefully this has cleared up the BGP attributes that we're looking at, right? The wait, the local preference, AS path prepending, and the med. And wait and local preference control 100% the egress outbound flow of traffic from your autonomous system. AS path prepending and med try to influence the ingress inbound flow of traffic into your autonomous system. But as we saw, you cannot control how traffic comes into your network with BGP, because the other autonomous systems where the traffic is coming through, they're going to have the final say. Because if they're using wait or they're using local preference, like I just showed you here, then everything goes out the door. Now, one of the last things I wanted to show you here is the image. So this is the image from our book, right? And it's a decent image, and it shows you the BGP table, and it gave you the different names that it's known by. And then you'll notice here, it shows you these arrows, like the incoming neighbor, and then it talked about filter and route maps, right? So it's like it shows you filter and route maps here, and then it shows you filter and route maps here, and then it shows you the main BGP table, and then it doesn't show you sort of the main routing table, right? But it would go, the best BGP route would come out of, and this is sometimes called the local BGP rib, LOC. Well, the single best path will get inserted into the IP routing table, right? Or the rib, when you say show IP route, right? But what I don't like is, I like that they give you the commands, right? I mean, this is fantastic that they give you the commands to run, but they don't talk about what these databases are here. And there's 2 additional databases that don't show here. This one right here is called the adjacency, or ADJ. And here, let me grab I was drawing with my mouse there, and that is just not working. The adjacency, and it's ribs, and it's plural, RBI and then little s, adjacency ribs in, because there is one of these per neighbor. That's how we can clear. We can also do a clear IP BGP per neighbor, right? In most cases, you're going to do it, for all neighbors. But if you just wanted to do it for one neighbor, you could refresh the adjacency rib in, or this is referred to as the adjacency ribs, RIBS, out, right? And basically what it is, the adjacency rib in, this is all of the NLRI, all of the routes that this neighbor is sending to me. And think of it as like a quarantine area or a staging area. So all of the routing information from this router will come into that router's adjacency rib in, right? On my router. My router keeps it in this little quarantine area, and then it applies all of my filters or my route maps, right? All of that traffic engineering, the policy that I'm applying, it gets done here, because maybe I filter some routes out, right? Maybe I don't want to get certain routes. And you've seen, like, in the adjacency rib out is typically what we've been dealing with, right? When we're using the route maps with the local pref, and so I should just say the local pref is internal, but the AS path prepend and the med, we're using the adjacency rib out, right? Because we're sending that in our outbound updates. So I apply my policy here, and whatever makes it through after the policy has been applied comes into the BGP local rib. And then BGP goes through its 4 million step, it's about 18 steps, goes through that 18-step process to figure out, hey, which one of these routes, if I've got multiple routes to the same destination, which one is best? And then the same thing is true. When I'm sending my updates out, like from router 6, when we did the 6 network or the 66 network, it's in this little staging area here, right? The adjacency rib out going to router 5, and that is where we set the route map. So we manipulate it before we send it out. So when you say clear IPBGP star out, you're refreshing, right? Or having policy reapplied and updates resent to all neighbors. When I said clear IPBGP star out. If I would have wanted a single neighbor, I could say clear IPBGP and then the neighbor and then star out, right? Or I'm sorry, and then out to send it to just, to refresh just one neighbor. But typically you're just going to do all neighbors because you want those updates to be sent to all neighbors. But again, you can do individual neighbors. And the same thing is true of the inbound. When I said clear IPBGP star in, I'm refreshing, right? And reapplying my policy to all of the routing information that I've learned that's kind of sitting in this little database right here in that staging quarantine area, waiting to see, hey, are we going to get into the BGP table, right? And the same thing is true here, right? I may be advertising 1,000 routes, and they're all sitting here in the little staging quarantine area, and it's not until all of the filters and route maps are applied, all the policy gets applied, that then they say, hey, am I going to get out of here? And okay, the policy's been applied. Yep, I'm able to, the policy allows me to go out and I'm going to go out, or the policy's filtering me out and I'm not allowed to go out. So you may be wondering, right? I can use a route map. I can use a prefix list. I can use a distribute list. There's all kinds of different ways that I can do layer 3 traffic engineering with BGP and apply policy. And so the final thing that I will leave you with is here. And this was a question that came up a number of years ago. I think it was 2017. Yeah, I think it's 2017. But the question comes up, well, okay, well, what if you have a prefix list and a distribute list and a route map and an AS path access list? Which one gets evaluated first? Like, how do you know, if you have those 4 things applied to one neighbor, right? How do you know which one's going to get applied first? Like, if you're filtering out stuff coming from an entire autonomous system, right? Maybe you don't want that first. Maybe you wanted that evaluated later. And you want to allow some routing information to come through, but then maybe not other routing information. So I did this video up here. And again, if you just Google, or not Google, I guess you could Google, or go onto my YouTube channel and say BGP inbound filtering order of precedence. And I actually walk through every different scenario. And for the release that I was using, which isn't that old, I show you that, hey, this is the order that things are going to be evaluated in when you're doing traffic engineering with multiple filtering approaches. All right. So, Kayla, let me ask you, since you stuck it out here for the last hour and 10 minutes, does this kind of clear up the BGP attributes and how you would use those attributes from a network administrator perspective to kind of control your flow of traffic outbound from your autonomous system, and then how you can try to influence the return flow or the ingress flow of traffic back into your autonomous system? And I'm hoping you're still there. You might not be there. That's okay. Okay, good. All right. Yeah, if you have any questions, let me know. And there are some, again, you can sort of freestyle with the Cisco Learning Labs, where I just reset the activity and then go in and test your understanding and your knowledge of things. See if you can, you don't have to do the activity as they have it set up. Try to go ahead and freestyle, maybe introduce a new loopback interface with a new IP address on one of the routers, advertise it, and then try to control where it's going and how you can apply the different policy. All right, well, let me go ahead and kill the recording here.